everyone, let's talk about logarithms. So logarithms and exponential functions are inverses of each other, and what we're going to try and do here is I'm going to show you that if you can do the exponents, logs are just sort of like going backwards. So if it says 2 to the second power is x, then x is 4. 2 to the third power is 8. And then this says 2 to what power is 6? And I'm like, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. So it must be something in between 2 and 3, but I don't really know what. It's not 2.5, so we'll come back to that one. 3 squared is 9, 3 to the third is 27, and then 3 to some power is 20. Again, it's got to be between 2 and 3, but it's not going to be perfect without, I'm going to have to guess and check basically. 4 squared is 16, 4 to the third is 64, and then you're like 4 to the x is 36. It's between 2 and 3 again, but we'd have to sit here and guess and check. Like I could try, like let's try, maybe I'll just get one of them. 4 to the, let's just start at 2.5. That's 32. 4 to the 2.6, 36. 4 to the 2.58. 4 to the 2.59. 4 to the 2.59. It's pretty close to 36, but see, it's going to take a while. So this is an approximation. Nearest tenth, it's about 4.6, but somewhere around there. Okay, we need a different strategy than guess and check, and that's what logarithms are for. So here's how this works. This is the main thing you need to be able to understand, is that these two forms are interchangeable. If I give you an exponent, you need to be able to write it as a log, and if I give you a log, you need to write it as an exponent. So the way I think of this is, if it's a base b exponent, then we read this as a base b log. And it's b to the x, so that goes over here. B to some power will give you y. Once you get used to rewriting this, logs are not that big of a deal. They're just exponents. You just have to kind of train your brain to see it. The base of the logarithm is always the base of the exponent. And then if it's an exponential form, you say b to the x. But in logarithm form, this is base, and this is base. Okay, y is their power. Okay, so that's the most important thing, is that the base is the same. So let's rewrite a couple of these. This says the base 7 log of 49. That's 2. Why does this equal 2? Because 7 to the second is 49. So the base 7 log of 49 is 2 because 7 to the second is 49. And I'm asking, what's the exponent? 2 to what power is 32? This is sort of like if you wrote it as an equation. 2 to some power is 32. 2, 4, 8, 16, 32. I'm making a table here for logs. This is 2 to the 5th. And that's because 2 to the 5th is 32. The 5, the exponent, is your answer. 5 to what power is 125? 5 to the third is 125. So that's what I'm going to start off with, is just rewriting it as an exponent and then figuring out what that exponent is. So if you see something like this, the base 12 log of 12, it's like saying 12 to what power is 12? 12 to the first power is 12. 12 to the first is 12. I'm asking you, what's the exponent? 12 to what power will give you 12? 3 to what power is 27? 3 to the third power is 27. 3 times 3 times 3 is 27. And the last one, anytime you have a log of 1, 23 to what power is 1? That would be the 0 power. So 23 to the 0 power is 1. That's true for any base. Okay, you can put any number there except for 0, and it will be the log of 1 is 0. All right, so common logs. When you see a common logarithm, that's what every calculator has. It's just going to be log. It doesn't have a base. So the base is implied to be 10, is base 10. Okay, it's implied to be 10. You don't usually write it there, but the base of the exponent is 10. And the other log that we use is natural log. And sometimes you can say that's base E. That's Euler's number. We talked a little bit about that. We did finance. But you could write it like as log with a base of E of x. Okay, so that's also on your calculator. The only button that's on everybody's calculator is the log and then the natural log. Those are on everybody's calculator. The fancy ones have base logs. But if you don't have a base, you have to realize this is saying the base 10 log of 100. So 10 to what power is 100, the second power. So the log of 100 is 2. 10 to what power is 10,000? Count the zeros. There's 4 of them. 10 to what power is 10? The first power. 10 to what power is... There's 7 zeros, so it's 7. 1, 2, 3, 4, 5, 6, 7. 10 million. So the 10 to the 7th is 10 million, so the log of 10 million is 7. And that's when you can use your calculator for. Log of 10 million. 7. All of these are, since they're on your calculator, you can just do them that way. But if you're relying on your calculator, log is never going to make sense. So don't just plug them in. This is the same thing, natural log, so it's base e. E to what power is e to the, that's implied to be 1, right? So then this is 1. The natural log of e is 1. E to what power is e to the third? The third. This is the 12th. This is the 578th. They cancel each other out. Okay, it's just like up here, you just count zeros. Here, the exponent is a base e, so it's base e. Now, you can start to make this tricky when you start to get to negatives and when you start to get to fractions. So these are going to be negatives because 2 to what power is 1 over 2. Remember, this means 2 to the negative first. 2 in the denominator means 2 to the negative first. So the base 2 log of 1/2 is negative 1. 2 to what power is 1 over 4? That's 2 to the negative second. So the answer is negative 2. You can say like 2 squared is 4, but since it's in the denominator, we need to move it to the other side. We make it negative. 3 to what power is 1 over 3 to the first? That would be the negative first. 5 to what power is 1 over 5 to the third? Because 125 is 5 to the third, this is negative 3. It's in the denominator. This doesn't have a base, so it's base 10. 10 to what power is 1 over 100 is 10 squared. So it would be 2, but since it's in the denominator, it's negative 2. Fractions. Okay, so 1/2 to what power is 4? Now this is 2 squared in the bottom, so I want to flip it. So we'll say this is negative 2. 1/3 to what power is 9? Well, 9 is 3 squared. So I want it to be 2 in the other side, so we'll say it's negative 2. 1/7 to what power is 7? Well, it's 7 to the first in the bottom, so we move it at the top, make it negative 1. 1/9 to what power is 81? 9 squared is 81. It's in the bottom, so make it negative 2. 1/5 to some power is 125. That's 5 to the third, so we make this negative 3. It's a little tricky at first, especially with your fractions and the negatives. Now, these are maybe the worst. These have different bases. So 8 to what power is 2? If I give you this without a calculator, what you have to realize is 8 has to be a power of 2. This is 2 cubed. So 3 to the 2 times what is 2 to the first? You're like, I don't know what that x is. But I can create a little equation here and say, if they're both base 2, then I have to set them equal to each other. 3x has to be 1, so x has to be 1/3. And hopefully you remember that 8 to the 1/3 is the same as the cube root of 8, which is 2. That's why this works. 49 to some power is 7. Well, you have to remember that 49 is 7 squared. And I could say, well, 7 to 2 times something is 7 to the first. Let's write a little equation again. 2x equals 1. So when you divide both sides by 2, you get x equals 1/2. And remember, 1/2 is square root. 49 to the 1/2 is the same as the square root of 49, which is 7. This one says 125 to some power is 5. 125 is 5 cubed. So we'll figure out that x by setting up 3x equals 1. X is 1/3 again. And that's because 125 to the 1/3 is the cube root. So as you get better at this, you might not need to write them out every time. You just got to say, cube root of 125 is 5. So the base 125 log of 5 is 1/3. Square root of 36 is 6, so that means this is 1/2. 36 to the 1/2 is 6. Another way of saying it, 6 to the 2x equals 6 to the first. 2x equals 1. So when you divide both sides by 2, you get 1/2. Last one, 1,000 to some power is 10 to the first. Well, 1,000 is 10 to the third. So I'll just write this as like 10 to the 3x. And again, it's cube root. 3x equals 1. So x equals 1/3. The cube root of 1,000 is 10. Now, there are some that are undefined. You can't take the log of 0. Hopefully you remember on the graph, logs have a vertical asymptote. Looks, oh, that didn't work. It looks something like this, okay? And it will never hit the y-axis. So there is a vertical asymptote here. But the reason why this is undefined is if I say 4 to some power is 0, you just have to realize that these are going to get smaller and smaller. No matter what I type in here, I'm never going to get 0 because exponential functions have a horizontal asymptote. Okay, so if I graphed 4 to the x, it would look like this. And remember, these decimals just get smaller and smaller, but they never get to 0. So this is not defined, undefined. And same thing here. If you raise 5 to a power, 5 to some power, it will never be a negative number. It'll be a fraction. It gets smaller and smaller as you make the fraction smaller and smaller, but it'll never get to negatives because it'll never get to 0. So these are both not defined. You can't take the log of 0, and you can't take the log of negative numbers. And if it helps to see it again on the graph, that's because on the graph, the domain is 0 to infinity. You can't take the graph of 0. It's not inclusive. You can't take the graph of negative 25. Negative 25 is over here. Okay? So we need to practice doing this with just simple numbers, and then we'll come back and do more of the fractions and the decimals. But go ahead and give your Delta Math a shot, and make sure you smash that like and subscribe.